All right, just 1 minute. We'll start the class. Oh, yes. Um, okay, so hello everybody. Uh, so welcome. Can you all hear me okay? All right, so my headphone just died a minute ago. So you might hear strange noises of birds and planes and so on from the window here. Apologize. Hopefully it doesn't bother you too much. Um, okay, so
Yeah. But before I start, I want to make an announcement that the time of the section has been moved to Tuesday because at Thursday there will be a condensed matter seminar starting next week. So now the section time is on Tuesdays from 4 to 5.
oh, okay, thanks, Tayu. Also, we had a nice discussion meeting yesterday uh, at 8 a.m. in the morning from just a few people, but several from different time zones. And I'm going to change that to 9 a.m. as I've announced on Slack. Hopefully you saw that. I think that was a great meeting. I hope more of you will come 9 a.m. Okay, that's legal time for Cambridge, so you should be able to come. With all, just an informal discussion on the previous lecture. All right, so now let me share the notes for this lecture. If I get everything right. It's not YouTube. Sorry. For some reason, all the technical part is, here we go. And then I share content screen. Start broadcast. Okay, you should be seeing my screen. And then now, okay. All right, so we talked about Fermi liquid theory last time. And I just wanted to summarize. The idea is that you assume that the structure of excitations or elementary excitations of a strongly interacting fermion system are basically the same as that of a non-interacting system. So the basic structure of non-interacting system is that there are these elementary particle and hole-like excitations which live near the Fermi level with vanishing energy. And the excitations above the Fermi level change the particle number by 1, and the excitations below the Fermi level change the particle number by -1. So we assume that's still the basic structure in interacting system, where you have these quasi-particles, which have total particle number 1, but really consist of a cloud of a bare particle surrounded by a cloud of particles and holes, so that the total particle number is still 1. And if spin is a good quantum number, then spin is still a half. This meeting is being recorded. Excuse me, what was that? Why did we hear that just now? I don't understand. Okay, could have been running. Okay, well, I'll just ignore it. And you can all hear me, right? Somebody speak up if you can. Okay, thank you. All right, so as I was saying, there are these normalized quasi-particle excitations, which are particle-like above the Fermi level and hole-like below the Fermi level. So the only difference from a bare particle is that their microscopic wave function is rather complicated, but we don't care much about it. But it has an characterized by a mass, which we call m star, which is different from the bare electron mass. And that's one of the main places where the effect of the interactions come in. Okay. Then, however, Landau pointed out that there's another place we do have to include the interactions more carefully. And that's in the second order term right here, this term over here, which changes the energy of a set of excitation depending on other quasi-particles that might be around. So this is one set of quasi-particles here, so here's another one, and their interaction also changes the energy. Okay. And then the basic argument was that this bare term, which is order temperature squared, is of the same order as the normalized term, which is also order temperature squared. And here I want to make one clarification, exactly how we are counting these powers of temperature. So delta N of P, maybe it's useful to plot delta N of P, see what it looks like. So here's N0 of P. Here's the actual N of P of the quasiparticles, assuming they exist even far from the Fermi level. But the difference between these two is only close to the Fermi level. So the fact that quasiparticles don't really exist out here doesn't really matter because they just cancel out anyway. But even for this plot, if you plot delta N of P, it looks something like this. Delta N of P. We just take the difference of these two curves. What's this P? Well, it's negative, and this is PF here. It's something very small, but it's negative. Then it has a jump of 1/2 and is positive over here. So this value, at least in thermal equilibrium, will be around 1/2. This discontinuity is exactly 1 because it's the discontinuity coming from this discontinuity. Okay, so the magnitude of delta N of P is of order 1 or 1/2 or something like that. But its width, this width here is order temperature. So what happens here when you do this integral, over here, you get a factor of T because the energy is of order T, and delta N of P gives you a factor of T because the integral extends over a region T. And here the same way, I mean, I somewhat misleadingly said this is of order T. That's not correct. It's when you do the integral over P and P prime that you pick up a factor of T from here and you pick up a factor of T from here. Okay. Yeah, all right. So then near the Fermi level, you define EP this way so that you get a definition of M star. Then for the specific heat, however, these interactions don't matter because for a thermal distribution, when you do this sum over P N of P, then you can see in this curve right here, the integral under N of P is just 0 in its for a thermal distribution. This part is approximately symmetric and anti-symmetric along the radial direction. So when you do the radial integral here, and you have to keep in mind that the F's don't depend on the radial direction, they only depend on the angular direction. So you can just do the radial integral and it just vanishes for thermal equilibrium. So you have this very important result that for the specific heat, the Landau parameters don't matter, and there's a factor of M star. I should notice, that there were a bunch of typos in the previous note, which I've corrected, and I've uploaded a new PDF on the lectures with the correct typos corrected. Okay, and then briefly I mentioned the compressibility. Well, the compressibility is different because what you're doing is you're adding a probe change in the chemical potential, and that has a different effect on the particles below and above the Fermi surface. So the interactions do matter. And this statement here is that, sorry, where's the statement? Where did it go? Okay, oh, I'm sorry. This is for the free electron gas here. That's a fairly simple calculation. Then here, right. So what is this this expression here about? So, so this expression here, this is coming from the fact that we're now thinking of the energy of a quasi-particle as really the variation of the energy, the total energy, with respect to the occupation number. So this is what gives you this result here. So you imagine, you have a bunch of quasi-particles sitting there. Then you change the chemical potential a little bit. Okay. And as you change the chemical potential, you'll create more quasi-particles. But those quasi-particles will interact with the other ones that were already there. So we're interested in the change in energy for each quasi-particle as you add it. And that change in energy is just the variational derivative of E. This E with respect to N of P, delta N of P, and that gives us the normalized energy of each quasi-particle due to the presence of the other quasi-particle. This is kind of like a mean field shift. So you add a quasi-particle momentum P, it has its own energy, but it also has a shift in its energy due to the presence of the other quasi-particle in momentum P prime. Okay, it's just like a first order perturbation theory, the interaction, if you wish. But of course, the F's are numbers that can be computed to all orders in perturbation theory. It's just some number, and that's all you need to do because of the fact that you only need to worry about quasi-particles right near the Fermi level. Okay, so now if you compute the change in density due to a change in chemical potential, due to the fact that the quasi-particles energy depends on the occupation number of the other particles. So when you had free particles, you had an energy EP minus mu here, and you looked at how that changed with the chemical potential. So EP went to EP minus delta mu. But now you have two terms. You have EP minus delta mu as before, but you have this other correction because the actual energy of the quasi-particle has this interaction term. Okay, so that's the basic expression there. And now you just have to do some algebra to figure out how much is the total change in density for each change in chemical potential. So there's some, you just expand in delta mu and you match left and right hand side and figure out what is the relationship between delta N of P and delta mu. So there's some algebra that I urge you to go through, that I won't go through. And there was again a typo in the previous note, which has now been corrected. So what you find is that the coefficient, the change in delta N of P depends on this number. It happens only right near the Fermi level. Has this independent number A. And the number A involves this F naught. So what's happening here is that every time you change the chemical potential a little bit, it changes the number of particles your electron, the quasi-particle interact with. And so there's this correction here coming from the fact that the quasi-particle energy dependent on the density of the other particles. So if you just solve that self-consistently, you notice delta N of P appears on the left and also on the right. But you can solve it because its dependence on P is very simple. It's just a delta function of the Fermi surface. So when you do that, you get the renormalized correction. This is a so-called Landau correction for compressibility. All right, that just gives you a flavor of the kind of things you have to do. And you could spend the whole course doing this in more detail and doing it in many different situations with all kinds of probes. And then there are books on that, but that's really not the purpose of the course. Okay. So, however, I do want to say a few more things about Fermi liquid theory. And so, yeah. So for that, let's understand a little bit exactly why Fermi liquid theory is valid. It's got nothing to do with the weakness of the interaction. The interaction can be strong. It really has to do with phase space considerations of what happened here from the surface. But having said that, let's just imagine that the interactions are weak. Okay. So imagine you have a quasi-particle sitting here at momentum k. And then, it interacts with other quasi-particles that might be around. So it gets scattered to some other quasi-particle at state at momentum k plus q. Now, in that process, it has to conserve energy and momentum. So there has to be some particle that moves, say, from k prime to k prime minus q. Okay. So let's compute this rate. How often does this happen? And we're just going to use Fermi's golden rule here and try to estimate how quickly this particle will be scattered. So Fermi's golden rule says that the rate of any process is a matrix element squared. Okay, we don't know what the interaction is, but we just assume it's independent of momentum and everything else. Okay. And then we write down the delta function for energy conservation. So this is the delta function for energy conservation, that the particle here with energy Ek, there was a particle here with energy Ek, there was a particle here with energy Ek prime, and they get scattered to particles here and here with energy Ek plus Q and Ek prime minus Q. And this must be zero because you're conserving energy. This is a real process with a real scattering event. You're talking about kind of asymptotic states in some S matrix language. And notice momentum is automatically conserved by the way we have parameterized these momenta. Because the initial momenta was k plus k prime, the final momenta is k plus q plus k prime minus q. So it's also k plus k prime. But the most important effect, so that's the usual things, but the fact this is a many-body system comes in from these factors. So what is this factor? So to begin with, we assumed there was a particle here, so that's fine. Now it must be that there has to be a particle present here. Okay, if there wasn't, then this scattering wouldn't be possible. So the probability of finding a particle present at this point is the Fermi function of Ek prime at that point. And then furthermore, they scatter into these states, these open circles, and those must be empty. So there must be 1 minus f of Ek prime minus q, saying that this state is empty, and 1 minus f of Ek plus q, that this state is empty. Okay, so now you have to do this integral over k prime and q. Everything is known on the right-hand side. You have to integrate over all possible states of this particle and all possible values of the momentum transfer q. And everything is taken care of in terms of energy and momentum conservation and Fermi statistics are all taken care of by these factors. All right, but that's a horrible integral. I think this is where, again, several pages of a book later, you might get accurate estimates of this because there's this k prime and q appearing in complicated places. So we're just going to make a drastic approximation, and let me just say that approximation, it doesn't get the prefactor quite right, but who cares about the prefactor? So the approximation we're going to make is that we can just ignore momentum conservation and just call these energies E prime and E double prime of this and this. And then, well, okay, I have skipped various steps here. Maybe I should show how that works. Right. Okay. I don't want to spend the whole lecture on this, but it's just a matter of doing these integrals. Let me at least write down one intermediate step, and then you can take it from there. So. Where am I? Okay. Right. Okay, so what we have here is if I take this expression, so I had, let's see, I hope, oh, sorry. K prime and q, I had something like 1 minus f Ek plus q. Then I had f of Ek prime. And then I have 1 minus f of Ek prime minus q. And then I had a delta function for energy conservation. Delta Ek plus Ek prime minus Ek plus q minus Ek prime minus q. Okay, so I'm just going to integrate over energies independently and just ignore momentum conservation, just to get a first estimate and to avoid lots of very messy calculations. So this I can write as dE1, dE2, dE3, 1 minus f of E1, f of E2, 1 minus f of E3 times delta function of E plus E1 minus E2 minus E3. Okay, times some factor due to factor from momentum conservation. So it turns out that that factor for momentum conservation, reduces the value of the integral a bit, but by some factor like pi or 2 or something like that. So let's not worry about it. It's not that crucial. All right, so now this expression here is find an integral you can do. So I urge you to write this out and try to do that integral. There's 3 integrals to do, but really only 2 because one is just a delta function, and you can work it out. And all I've shown here is what happens in the 0 temperature limit when you put in all the constraints from the Fermi functions. When you do that, you get this integral that you can even do right away. And when you do this integral, you find that this gives you an E squared. So this is the most important result here that I want to focus on. At least at 0 temperature, the lifetime of a quasiparticle diverges as 1 over E squared as you approach the Fermi level. And if you do this at the Fermi level, well, of course, it's 0 at 0 temperature by this formula. But if you do it at finite temperature at the Fermi level, then the lifetime divergence is temperature squared, 1 over temperature squared. So as you come closer and closer to the Fermi energy, the lifetime goes to infinity. But as you know, that the natural question is not what is the lifetime going to infinity. It's the question of what is the value of the relative value of the inverse lifetime with respect to the energy itself. Okay, so the energy of the quasiparticle, let's see that here. Yeah, okay. The energy of the quasiparticle also vanishes on the Fermi level, vanishes as epsilon. So the energy, which is of order epsilon, is much, much bigger than 1 over tau, which is of order epsilon squared. So this is the key thing, that as you approach the Fermi level, the lifetime effects are much smaller than the energy effects by an additional factor of energy or temperature. And that's why Fermi liquid theory is valid. This is the essential calculation, the reason why Fermi liquid theory is valid. And you notice that this fact that it becomes small has nothing to do with the interaction strength or any such thing. It's entirely coming from the phase space factor, meaning the energy conservation factor and these Fermi functions. And so it's quite universal, nothing much than Fermi statistics. Now it turns out that if you carefully do these integrals, these radical assumptions I've been making are not valid in 1 dimension. But they are valid in 2 and 3, and I'm not going to prove that. There's just a lot of mathematical analysis involved with that. So in 1D, we'll find later that Fermi liquid theory does break down, but not in 2 and higher dimensions. Okay, at least for a generic interacting Fermi system. So that's one important point for this lecture. Any questions? Okay.
Yes.
Yes.
Sorry. So what is the influence of, like, because here we are considering like a process involving like basically two scatterings, right? But in principle there can be like more of these processes. So is this
yeah,
higher?
So you could imagine that. Yeah. So if you imagine, so here effectively what's happened is that you have a process where your particle went from here to there, and you created one particle hole pair, because this went there and the particle went there and there was a hole here left over. So your particle came by, it got scattered and created a particle hole pair here. Now you can imagine another process where your particle comes by and creates 2 particle hole pairs or 4 particle hole pairs. Those are all allowed processes at some high order in perturbation theory. What you'll find is when you create 2 particle hole pairs, this result here goes with epsilon to the 4th. It's even weaker. And if you create 6, it goes with epsilon to the 6th, and so on. 3 particle hole pairs, it goes with epsilon to the 6th. So higher order processes, at least real processes, higher order processes like this, which create more and more particle hole pairs, don't contribute to the lifetime at all.
I see, but they're not higher order in the interaction, right? Because the interaction is in mu squared, which remains the same?
No, there
or-
will be higher order interaction, but we don't want to use that because U need not be small. U could be large. We don't want
Right.
to use that factor. We want to use just temperature and Fermi energy and the energy of the quasi-particle as the suppression factor.
Right. So when you say that these processes are higher order, the order is like the energy power.
Yeah. So let's say the typical energy of a quasi-particle is temperature. Let's think of that way.
Yeah. Yes.
They're higher order in temperature. Maybe temperature to the square, temperature fourth, temperature sixth. And as long as your temperature, so we assume that your interacting Fermi system is characterized by some energy, which is usually pretty large, 1 electron volt or something. There's a Fermi energy, which is few electron volts. There's some interaction energy, which is also electron volt, which is 11,000 Kelvin for a metal. And your temperature is, 300 Kelvin. So that's the expansion parameter, temperature divided by the Fermi energy, which is quite small for ordinary metals.
I see.
But where we need perturbation theory of the interaction is computing the value of m star or computing the value of this f. Suppose that you ask me, what is the value of the f? This f here. Unfortunately, I can't. There I have to use perturbation theory. I cannot compute it. I have to use a computer to do that. Because in principle, all order is interaction. So similarly, what you might guess, at least for small momentum scattering, well, that this U has to be replaced by the F's, some combination of the F's. But that's not easy to compute.
I see.
But in any case, this effect here is beyond Fermi liquid theory. In Fermi liquid theory, you just put tau equals infinity. In precise Fermi liquid theory, this is going beyond Fermi liquid theory. Because it's a correction that's not included in the Landau function.
I see. And the G is the like a phase space density, or sorry, the
yes,
G of
yes, it's the density of state, correct. So when you convert the momentum integral to an energy integral, you pick up a factor of the density of states at the Fermi level. Yeah, I should have written that here. So when I went from here to here, so really the way I should write this is the following. This will make it hopefully even clearer. Let me put, there are 3 momenta here, so let me write this in a better way.
Yeah.
Well, okay. Yeah, okay. So let's say this is K, Q. Well, it was integral over K prime and Q, so I didn't write this properly. K prime and Q and K double prime. So let's see if this is K double prime. Yeah. Then there should be another factor of momentum conservation. So let's see, K plus K prime must equal, so delta of K plus K prime. This is not the best notation, minus K minus Q minus K double prime. So that's, so now I have 3 momentum integrals here with an extra momentum conservation delta function. I just ignore it. And then when I convert this integral to an energy integral, I'll pull up a factor of the density of state cubed. Okay.
Thank you.
Okay. All right. So one final thing I want to say about Fermi liquid theory.
Sorry, one thing. How does this ever break down if it doesn't matter on the if the scale of the interaction doesn't matter? Like, is some perturbation theory in like U times T over EF, no? Or
right. So the statement is that to all orders in perturbation theory, Fermi liquids are stable in 2 dimensions and higher. So anyway, so if you found a non-Fermi liquid in 2 dimensions or higher, which we will find eventually, it has to be a non-perturbative effect. It has to come from some beyond, something beyond Feynman diagrams. When everything I'm doing here is really perturbation theory in some, I assume an assumption of adiabatic continuity. Sorry, that's really what I assume, that smoothly varying from the non-interacting problem to the interacting problem didn't involve any sharp changes, which is equivalent to saying that perturbation theory is okay. So this is all a statement about perturbation theory, really.
So
and-
a non-Fermi liquid, you'd have some sort of like, there's zero radius for you to tune some parameter, or like there's some finite radius after which you can't, you
No,
cross
so
it.
what this proves is that if you had a very weak interaction, you cannot find a non-Fermi liquid. But it doesn't prove that you couldn't find one for strong interaction, because I haven't shown you anything about the radius of convergence. It could be the radius, you know. So these arguments prove that the radius of convergence is not zero. It's something finite. You have to go somewhere near.
Okay.
And it turns out when you take these arguments more carefully in one dimension, you find the radius convergence is zero. So we'll get to that later. Okay, so right, so I'm going to use a little bit of Green's functions here, and for those of you who haven't seen Green's functions, well, don't get scared. I mean, all we're looking at here, just a convenient way to talk about it. So you look at a Green's function, which is the amplitude for creating a particle with momentum k at a point, and then annihilating it time tau later. Then you take a Fourier transform of that, and so let me do this in the piece of paper. Yeah. Okay. So if you create a particle, z dagger k at say time 0, and you annihilate it at time t. Well, that's just going to propagate, and it has some energy. And so if you have a quasiparticle, you just create a quasiparticle. It doesn't care about the rest of the environment. It'll be just e to the minus I e k t. Okay. So now the Green's function is just the Fourier transform. So g of omega is this quantity dt e to the I omega t of this quantity here. And so that will be something like 1 over omega minus ek. Okay, so what you see is that if you have a perfectly long-lived quasiparticle, then the Green's function g of omega at momentum k will have a pole at omega equals ek. This simply comes from the Fourier transform of that. Now the particle we saw had had some lifetime. So if it has a lifetime, you might say, well, then maybe there's an exponential decay here. So this is called, and then you also put in a prefactor, which is called the quasiparticle residue. So this is the QP residue. And this is the lifetime. Now there's all kinds of subtleties here with time-ordered Green's function versus Feynman Green's function. Again, that's a whole long course. I don't want to get into any of that. It's really not that important for anything we're going to consider. Just want to say that there's if you imagine this very simple propagation and you just integrate this from 0 to infinity, that's an integral that's perfectly well defined. What you'll get here plus I over, well, it turns out, yeah, tau k, where tau k is the quasiparticle lifetime. So what we see is that the Green's function has a pole which has gone off slightly off the real axis by a tiny amount. So if this is your complex frequency plane, there's a particle like over here, where ek is greater than 0. So this is the pole. This is at ek, and this is the, well, sorry, it should be below the real axis. Sorry about that. Somewhere here. And this distance here is 1 over tau k. Okay. All right, so that's how you would formalize what I've just told you in terms of the Green's function. Okay, so that's something I've done over here. All right, so this is the Green's function written out with a quasi-particle residue. Now this is written on imaginary frequency for technical reasons. You can do it on real frequency too. And this is the lifetime. And it turns out that for this particular imaginary frequency Green's function, there's a sine omega here, which because the lifetime comes in with the opposite sign for particles versus poles. Anyway, so using this kind of Green's function, you can then try to compute the momentum distribution function of the bare quasi-particles. Okay, so this is in general quite hard to compute and has all kinds of contributions, but you can argue that those contributions are in the end smooth functions of k. So what happens is that if you look at the momentum distribution function contribution from this pole-like contribution of a quasi-particle, which is very near the real axis, the fact that the lifetime goes to infinity and the pole touches the real axis right at the Fermi momentum, gives you, when you take all the convergence factors into account properly, gives you a discontinuity precisely at the Fermi momentum. So recall that if I had free particles, n of k versus k was just that. So what's happened when you include interaction, the n of k is no longer just a simple step function like that. It's got a smooth background contribution, but it's still got a step. And the height of the step is not 1, it's the quasi-particle residue z, which is between 0 and 1. So that's like sometimes called a wave function renormalization or quasi-particle residue, which tells you that there are zero energy excitations. Okay, so another important thing to keep in mind here, this is something happening at kf, some large momentum, and n of k is the integral of the Green's function at all frequencies. So what that means is that it involves contribution from excitations at all energies. It's not a zero frequency or long time quantity. It's a short time, equal time quantity. N of k is just equal to expectation value of c dagger k, ck. These are, you annihilate and create a particle at the same time. So it's an equal time limit of the Green's function, which is why there's this integral over frequencies. So you're looking at contribution from all possible energies. But most of the high energy excitations only give you a smooth contribution. In fact, all of them. But there is a zero energy excitation, which gives you the discontinuity. So even though you're looking at equal time quantity, it is sensitive to a zero energy excitation, which gives you discontinuity on the Fermi level. Okay. You need that much later in the course when we talk about non-Fermi liquids, where we will also develop the needed technology using path intervals, which we haven't done yet.
Sorry, Subir,
Okay.
can I ask a question?
Yes.
So I'm confused about where the plus I omega squared sine of omega term comes from. Is that like, adding an I epsilon underneath the propagator to make sure that it's time ordered, or is it something else? I didn't understand your explanation.
I didn't give one, so good. Thank you for asking. So first, let me talk about the omega square. The omega squared is easy. The omega squared is just the same as this e squared here. Okay. The inverse lifetime goes as energy squared. Near the pole, omega and e are the same, so I may as well put it omega squared. The more subtle part, which I haven't explained, is why is there a sign? And that has to do precisely what you mentioned. It has to do with the time order Green's function and exactly how particles and holes contribute to the time order Green's function. This happens to be, in fact, a retard. Which is this? I believe this is the retard. I don't even know which one this is. G of I omega. This is This is the time-ordered Green's function in imaginary time. And for that time-ordered Green's function, the lifetime appears with the opposite sign for particles. It's related to the fact that the energy of the particle itself is also negative, so the lifetime also has to come with the opposite sign.
Perfect. Thanks so much.
Okay, and then you just take this and do this integral with some contour integration, and you'll see that there's a discontinuity. Other questions?
Yeah, sorry. Could you say once again, like how you mentioned that the zero energy excitations basically cause this jump to be reduced? Could you say that again,
Okay.
or like?
No. So so n of k is an equal time correlation function. It's C dagger and C at the same time. Okay. So in Fourier space, this means n of k involves excitation at all energies. Okay, and you can see that here because you're taking the integral of the Green's function at all frequencies. Okay. However, this discontinuity is only because there's this pole in the Green's function that happens to hit the real axis. Okay, so as what happens is that if you look at this pole, at least in this time of the Green's function, the pole comes in from the lower half plane and goes into the upper half plane and hits the real axis. So and it hits the real axis precisely when k equals kf. Okay, so that's a zero energy excitation. The pole will hit the real axis when k equals kf. So that's a zero energy excitation. It's only because the pole crosses the real axis that you get a discontinuity. Because on one side you close the contour this way, the other side you close the contour the other way. And so there's a big difference whether the pole is in the upper half plane or the lower half plane. And it's the only fact, it's because the pole is going through the real axis that there's a discontinuity. And so the discontinuity is a measure of zero energy excitations. So there's a non-analyticity in n of k, which tells you that there are zero energy quasi-modes. Okay, it's kind of a formal point. If you got lost, don't worry about it.
Thank you.
I'm so sorry. Can I ask another question about this?
Please go ahead.
Yeah. So why is there? So if you included instead the exact prefactor in front of omega, or sorry, omega squared sine omega, would you get like an observable shift in z? Because when we calculated the lifetime, there was this overall prefactor. You wouldn't see there would be no.
You could put any constant here; it won't make any difference. You can put any number here you want. It will still have the discontinuity will be given by this factor. It's the residue at the pole that matters.
I see.
And the pole at zero energy, and that pole, at zero energy, the pole is at, this is also going to zero at that point. So this is going much faster to zero, so it doesn't matter at all.
Okay, thanks.
Yeah, if this omega squared wasn't there, then some of the things you're saying would happen. It would depend on this number, but because it's at omega squared, it doesn't affect anything.
I have a question.
Yes.
What's the difference between this n of k and the n of p that we had at the beginning of the lecture?
Yeah, so this is the n of k for the bare electron. This is the bare electron operator. Good question. Thank you. Whereas this n of p here, which we just took as a Fermi function, pretty much, is the n of p for the quasiparticles. Okay, so there was no factor of z or anything floating around here, because we were just talking about whatever the particles were. We didn't care, what the actual wave function was. It's some complicated object, but it's a fermion and it has a certain energy, so it has to obey the Fermi distribution function, basically, and no other choice. So this n of p here was the quasi-particle distribution function. So we put that to make sure you p, whereas this is really the electron, the bare electron n of k. And even at zero temperature, so that's right. That this is n of k. These are the electron n of k. So the electron n of k has a discontinuity which is less than 1 and has some unknown smooth part. Okay, So the electron n of k has a smooth part here, and a smooth part here, and a jump at 0 temperature. The quasiparticle n of k, whether you do the subtraction or not, has a disquantity which is almost exactly 1. So this distance here, from here to here, is exactly 1. Because here we were talking about renormalized particles, quasiparticles, and here we're talking about bare particles. So what what can happen is that what will happen in a very strongly interacting theory is that Z could become very small. If you take some heavy fermion compound, some of the rare earth transition metal compounds, Z could be as small as 10 to the minus 3 because they're very strongly interacting. So Z can become very small. But that doesn't mean Fermi liquid theory is not valid. It still could have a wide range of validity because Fermi liquid theory only cares about this term. Whether it's valid or not cares how large this term is. As long as this term is small, you're fine. So whether Z is small is not a good measure of whether your Fermi liquid theory is working well. It's just telling you what's the overlap between the bare particle and the renormalized quasiparticle. It doesn't say anything about the stability of the renormalized quasiparticle. Okay.
But
Go on, sorry.
no, so in this sense, like whether the quasi-particle picture is like still valid in a sense that the decay rate is like appropriately small.
Mm-hmm.
But for example, Z is very small, then we basically don't see Fermi's surface anymore.
You wouldn't see photo emission experiments where you actually measure. So if you did an experiment to measure the momentum distribution function, yeah, it would be hard to see it. But there are many other experiments you can do which can detect the Fermi surface. You may know that there's something called quantum oscillations, which tell you how the resistance oscillates in the magnetic field. But there are other very clever experiments which measure other quantities which don't involve measuring the bare particle. But they're effectively all, the electrons basically remain in the sample. To measure the momentum distribution function, you have to do something like you send in the beam of, it's a photoelectric effect. You send in light and an electron comes out. But what comes out is a bare electron. A quasiparticle doesn't come out of the sample, it's just a bare electron. So for that, yeah, the Z will matter. But there are other measurements where the electron remains in the sample, like quantum oscillations. Then they won't care about Z. You could still see a Fermi surface very beautifully in quantum oscillation, even though Z is really tiny.
Oh, so you can see like bare electron Fermi surface, but like I thought that if Z is very small, then this plot here is basically smooth.
No, I think the correct way to think about it, if there's a Fermi surface, which is a quasi-particle Fermi surface.
Right. But in terms
that's perfectly well defined with a discontinuity of 1 in any Fermi liquid.
Yeah.
And if you did an experiment to measure the quasi-particles directly, rather than measuring the bare particles, you would see a beautiful Fermi surface. But if you did an experiment which involved ejecting a quasi-particle out of the sample and converting it into a bare electron, then you'd be in trouble.
So one thing is there some interpretation of the Z in terms of some overlap with the bare and the quasi-particle?
Yes, absolutely, there is. I think that involves a lot of Green's function technology. I'd rather not go into that.
Okay.
I'm already, this lecture was supposed to be about superfluids, but it's almost done. Anyway, no, it's good. It's good to get a good understanding of Fermi liquids. Especially, I want to open, the questions have been all from a few people, so others feel free to chime in if you have questions. And of course, I'll continue to have a discussion tomorrow morning at 9. Okay, it's Saturday morning, but anyway, I'll be available on this. All right, let me get in a few words then on the next chapter. Okay, there is some, in the notes here, there's some discussion of the Luttinger relation, which is something I already mentioned, that the value of Kf, or the volume enclosed by the Fermi surface, is not renormalized by interactions. There's a proof here which is really complicated and involves lots of horrible Green's functions, and then refers you to some other paper. But really, eventually, if my plan, everything goes on to plan, give you a much more elegant proof later in the course. Okay, so we have talked about interacting fermions in, well, strictly speaking, 2 and higher dimensions with arbitrary interactions. And we came up with a kind of very generic answer. What interacting fermions do, quite generally, is form of Fermi liquid. This was one of the great triumphs of many body theory in the, I don't know, 1950s and 60s. And it works beautifully in so many metals. And so for the longest time, people thought that's all there is. Okay, we won't, starting the 80s, people realized that's not the case. But before we go to fermions, let's talk about situation with bosons. And for bosons too, there's a very similar kind of story. What do bosons do at low enough temperatures? Of course, for many years before the advent of ultra-cold atoms, we didn't have a way of making the lab just a gas of bosons or a dilute gas of bosons. I mean, you have helium-4, that's really, but it's a very dense gas and strongly interacting. Now we have ultra-cold atoms, and we have lots of other beautiful experiments, and we can look at all kinds of interacting bosons of various types. So now you can ask, suppose you had a gas of bosons, what is it going to do at low enough temperatures? Well, the answer already was discovered by Bose and Einstein. Well, I guess it was really Einstein who first found Bose-Einstein condensation. They, at least weakly interacting bosons, undergo non-interacting boson. This is what Einstein found, undergo Bose-Einstein condensation. And that was all. That was, I think, 1915 or something like that. And it wasn't until, I don't know, again, I don't know the dates, 1950s or so, when Bogoliubov found that, extended that theory to weakly interacting bosons, which is sort of the analog of the Fermi liquid theory, the fermions that we just talked about. And today we understand that that theory, in the same sense as Fermi liquid theory, is actually valid even for very strongly interacting bosons. It's perfectly fine as long as perturbation theory is valid and you're in the superfluid phase. So what we want to do now is just understand what's different for bosons and how for weak interactions you do get superfluidity and what is the characterization of superfluidity. So that's going to be the next. And then superconductivity, which is a very closely related phenomenon that we'll talk about also next week. Yeah. So all these statements that I'm making, today they sound totally obvious, that superfluidity is the same as superconductivity, weakly interacting Bose gas is the same as strongly interacting Bose gas as long as a certain symmetry is broken, as we'll see. These are regarded as obvious statements, and I'll try to explain them, but historically they took, I don't know, over 20 years of arguments, and maybe even more, people agreed on these facts. But today there's really no doubt that just small corrections to the original Einstein-Bose theory of Bose-Einstein condensation really give you an understanding of all superfluids and superconductors in some basic sense. Okay, so let's take I'm going to present the Bogoliubov theory now. Okay, I'll just state the Hamiltonian anyway. So here's a bunch of bosons with some dispersion epsilon of k and momentum k. So Bk is a boson annihilation operator. For convenience, we'll take E of k to be E of 0 to be 0. So E of k is usually k squared over 2m. And there's some two-body interaction, which we take to be a contact interaction. So in terms of the actual first quantized Hamiltonian, this is the simplest possible thing. It's something like minus h bar squared grad squared over 2m, sum over all particles, plus 1/2 sum on I and j u naught times delta of Ri minus Rj. So there's just a very short range repulsion with a delta function between the bosons. And this is sum over I. So this is the Hamiltonian. If you take this Hamiltonian and write it in second quantized form, you'll just get this. Okay. So this u naught is the same as the u naught. This u naught is the same as this u naught. All right. So we want to understand something about the effects of u naught at zero temperature. We'll be in zero temperature for this discussion. All right. If u naught was 0, what is the ground state? Well, you just put, this is the Bose-Einstein condensate at zero temperature, which is the most trivial state. You have n0 particles. You take all your particles and you put them in the zero momentum state. But once you have some interaction, that won't be true. There are going to be some particles even at finite momentum, because these particles will repel each other a little bit, so they don't want to be all in the zero momentum state. And Bogoliubov showed us how to compute things for weak interactions, and that's what we'll talk about next week, both in the this kind of canonical particle language, but also in the path integral language, because this is one place you can do both, and then that'll get you a little more comfortable with path integrals, which how you covered in section on yesterday, I guess. All right, I think that's 4 o'clock, so I will stop there. And yeah, further questions on Fermi liquid theory? Yeah.
Subir?
Yes, please. Someone who hasn't asked a question yet, preferably, but go ahead.
I had 2 questions actually. One, the discontinuity in N at KF,
Yeah.
that's only sharp at t equals 0, right?
Correct.
At non-zero temperature, is it kind of just smoothing out? Does anything special happen to it?
Yeah, it becomes acquires a width of order temperature squared.
I see. Okay. Gotcha.
Oh no, sorry. Maybe it's order temperature. Excuse me.
And is that width, is it related to any of the quantities in Fermi liquid theory, like the F parameters or like the lifetime or anything? Or?
Well, just putting the Fermi function will also give you, the width of order temperature, even for free particles. The discontinuity disappears. So that's probably leading effect. Yeah.
Gotcha. And then also, you mentioned that before the 80s, people kind of thought that this was the end all be all of metals.
Well, modulo the BCS theory of superconductivity, we'll talk about next week. But yeah, the people really thought, okay, we've understood Fermi liquids, we've understood superconductivity, solid state physics is over. And you certainly had statements. In fact, even when I was in graduate school, like people making statements like that.
Gotcha.
Luckily, that's when the quantum Hall effect disappeared and was discovered, and those statements stopped. But
is there a good place to read about the work that led up to that, like the people trying to confirm Fermi liquid theory in metals?
Well, I mean, that's Ashcroft and Merwin is a good place where they don't really go into Fermi liquid theory, but they talk about a lot of the experiments just using free electrons, which confirm many details of this. And all you need to know for many of those experiments is that the main effect of Fermi liquid theory is to change M to M star and sometimes give you an additional renormalization factor.
I see. If
you want to study all the renormalization factors, I guess the biggest test of that was in the study of liquid helium-3, liquid helium-3.
Gotcha.
And there's a book by Wolfley and Volhart on liquid helium, huge backpack book, which is all about complicated tests of Fermi liquid theory and liquid helium-3.
Gotcha.
Yeah.
Thank you.
Sure.
I have a question.
Yeah, please go ahead.
So at finite temperature, if the bare N of K becomes smoothed out, and the reason there's a discontinuity is because of closing the contour in the Green's function above or below KF, then how can we see that at finite temperature this would it like change the Green's function or something? That this would smooth out the distribution?
Well, there's two effects, right? So when I go back to this expression here, so there's the fact that the lifetime, there's two effects. The lifetime would, of course, be temperature dependent, but that's a secondary effect. But there's another effect that the frequency summation has to be replaced by a frequency integration has to be replaced by a frequency summation. And that will give you all kinds of factors of Fermi functions at various places when you do the integrals. I think that will round this up. That will be the more important effect. This is really not, if you know what Matsubara frequencies are, you have to sum over Matsubara frequencies.
Okay, thank you.
Sure.
I have a question.
Sure.
So from the bare energy, the discontinuity, how do we infer that there's a non-zero excitation for the bare particles?
You don't. I mean, so let me make the statement again. So say you're as an experimentalist, you go in and measure N of K. And at low temperatures, and you see this kind of function. And you can measure at different directions, and in all directions, you will see this N of K having some kind of discontinuity. So the place where the constant discontinuity is, that tells you that there's a Fermi wave vector. It tells you, so by measuring it in different directions, you can even work out the shape of the Fermi surface. And this is something, photo emission experiments do this on a daily basis today.
Yes.
Okay. And then you can also measure photo emission with this. And this tells you something about the quasi-particle residue. So what I was saying was that what you end up measuring here, let's think in terms of photo emission. So photo emission, you send in a beam of light and you measure the energy of the electron coming out relative to the Fermi chemical potential. Okay. Now, and you can measure it, you can do at different, you measure the energy of the electron coming out as all different energies. Now, if you want to get N of K, you have to integrate over all energies to get N of K in photo emission. You just look at what you do in a photo emission experiment, you actually measure this quantity, omega is determined by the energy of the electron coming out, and you integrate over all energies to get this equal time correlation. So you're integrating over all energies to get N of K. What you'll find if you look at your data a little more carefully that the discontinuity, well, no, I'm sorry, this is, scratch what I just said. That's not, because this is, photo emission, what you measure is the imaginary part of the Green's function, not the real part. So that's a little tricky. But let's see. Yeah, no, photo emission, and also you never get the negative energy, so it's complicated. Okay, let me start again. So you can measure KF by seeing this discontinuity N of K. And my statement was that the discontinuity, the question, how do we interpret the discontinuity? What is this telling us? Well, the discontinuity is telling you that this KF is the location of zero energy excitations. At K equals KF, you have zero energy excitations. And the structure of how doing this integral kind of makes that clear. So let me try to, where's the piece of paper? I guess I need another paper. So let's look at the pole of this expression here as a function of K. Okay, so we just look out where the poles are as a function of K in the omega plane. And I'm just going to cheat and tell you what I think the answer is, although I'm sure that's correct. What you'll find is that, let's see if I can even get this right. So when K is greater than KF, the pole is at omega is equal to, well, yeah, so you have to analytically, yeah, okay, all right. You're doing the integral, okay, left, okay. The omega is equal to, we have taken imaginary time Green's function, I'm sorry. Where, okay, omega is equal to I VF K minus KF. So if you ignore this term, the pole is crossing, it's going from here to there. But let's imagine it goes something like this. The pole moves this way. This is, let's say this is for K greater than KF. I'm just randomly picking a sign here. And this is for K less than KF. And right at the K equals KF, you're at the origin and it goes right through 0. So you're doing some integral on some contour like this. So when you're doing the integral on, and maybe your magic closing the contour this way, then as you do this integral, on one side you pick up the contribution of the pole, on the other side you don't. So when it crosses the real axis, there's a jump, because on one side the pole is inside your contour, and the other side it isn't. And so because of that, therefore you get a discontinuity. And so the change, this discontinuity happens precisely because the pole goes right through 0 at K equals KF. And the position of the pole is precisely the energy of the quasiparticle. That's what the pole, that's what we showed a bit earlier. We showed here that the pole is just the energy of the quasiparticle. And so this fact as a discontinuity at KF tells you that there's a 0 energy quasiparticle there, even though the quantity you're measuring is not a 0 energy quantity. Because higher energy excitations cannot give you discontinuity unless they happen to cross the contour, right? And they only cross the contour right at 0 energy.
Okay.
Yeah, I have to apologize. This is not entirely self-contained, and it's the kind of thing, to do it properly, you really have to develop a lot of Green's function technology, which I don't want to. Because we're not going to need it, and that's not really the purpose of this course. 295B does a lot of that. Here, hopefully, just the object of this, like these 2 lectures, will just give you a flavor. You should really understand. This is an important argument that you should hopefully have absorbed. This argument here, and also these arguments here, which led up to the Landau function. And those are really not very complicated mathematically. They just involve a lot of, inspired guesswork really in the end, which is presumably what Landau did before things were checked by more complicated Green's functions. But we don't want to get there. Yeah, but you're right. I need to. Nevertheless, this whole argument should be cleaned up with some, at least, self-consistently defined Green's function with all these integrals worked out. I'll try to do that and update some better notes by the end of the term on that.
Thanks.
You certainly find a lot of this in many, many textbooks, so, with all the signs correct.
Can I ask another question? If you
Yeah, go ahead, Andrew.
Okay. So the non-perturbative effects you're referring to is presumably at z equals to 0. So how would we write the Green's function then for the non-perturbative effects?
Well, that's the big question, of course. We need a theory for a non-Fermi liquid. We don't have one yet, so we'll talk about it later. So the first place where we develop a way to do this is 1D, where we have something called Luttinger liquid theory, which involves learning something about bosonization, which we'll hopefully get to in a couple of weeks, 3 weeks. Yeah, but to do study of non-Fermi liquids in higher dimensions, well, you need a theory for why it's a non-Fermi liquid. It has to involve some kind of non-perturbative effects. Simple diagrammatic perturbation theory in interaction is not going to give it to you. That's clear.
So is the idea to just have like a coexisting state with other phase, or we want to like come up with entirely new fermion theory?
Well, I mean, it won't be a Fermi liquid. It's some other quantum phase of matter. So, we have, the idea here is, you have some big phase diagram as a function of some coupling constants. You have some coupling constant U1, U2, and when there's some region here where the ground state is a Fermi liquid. Maybe there's another region here where it's a superconductor or something like that. But so maybe there's another region here which is non-Fermi liquid. So how do we understand that? Well, we'll get to that, but we have to use entirely different methods. If you start here and try to go there, it's not so easy. You will just end up in the Fermi liquid. So you have to develop some other methods for understanding strongly coupled many-body systems.
Okay, thank you.
Yeah.
I have a
I mean,
question.
even in particle physics, it just turns out if you take the standard model of particle physics, in the end, it's once you know the particle content, everything they study when they study the standard model is essentially perturbative physics, with the possible exception of confinement. But even that's kind of understood in perturbation theory because you have this, no matter how weak the non-abelian gauge force, it eventually does confine. So you can see the fact that it's running away to confinement even at weak coupling. So here we're talking about a much more complicated effect, that there could be a strong coupling, entirely new phases which you have no inkling of at zero coupling. So we need some other methods entirely. So we'll see what they are. We'll slowly develop them as we go along. The simplest case would be 1D, where it's a quasi-perturbative method that's been developed. Yeah, there was another question.
Yeah, in the expression for NE of K that you were on before.
Which expression? Yeah, this one, right?
Yeah, what's in the exponent next to omega?
Oh, that's just 0 plus, so the infinitesimal quantity. That has to do again with these subtleties with time-ordered Green's functions and not. This tells you the fact that 0 plus tells you that the 0 plus tells you that the C dagger comes after the C. If you put a 0 minus, it will be C dagger as opposed to C dagger C. So ordering of these operators. So this is a positive infinitesimal.
Got it. Thank you.
Sure.
I have another question.
Yeah.
So you mentioned like we're using arabitic principle here, right? We're going from like a degenerate, non-degenerate ground state, where like you have a unique ground state in Fermi gas, and you're like tuning some interaction. So I was wondering, like, if you know that some state has a non-degenerate ground state, a degenerate ground state, so like more than one ground state, are you like can you rule out Fermi liquid theory by that? Because we're using like arabitic principle to connect Fermi gas to that.
I don't know if you can rule it out, but I mean, are you talking about, this the whole question is a little subtle here because this is a system with zero energy excitations, very low energy excitations. Because at the Fermi level, there are zero energy excitations. So what you even mean by the ground state is a little subtle and depends on the boundary conditions. You have to put this, take this, because in a truly infinite sample, there's no meaning to the ground state because there are infinite number of zero energy excitations too. So to really carefully define this, you have to put the system. This is what's called a gapless system. So I think you're coming from, some intuition based on gap system, where there's a ground state, there's a gap, and there's all the excited states. That's not the case here. The excited states come all the way to the ground state. And so what's a ground state, what's an excited state, is a little bit subtle and depends on your boundary conditions. So that's point one. So the degeneracy of the ground state can even depend on the boundary conditions. But that said, suppose, in fact, this will turn out to be quite crucial. Suppose you put your system on a torus or some periodic boundary conditions. And then you found that there were lots of low energy states, and you could account for all the low energy states, imagining that these were quasi-particles put in the same box. So you imagine you have a Fermi liquid, you have a ground state, you have some quasi-particles. You just put the quasi-particles in a box. It's easy to put a quasi-particle in a box. You just have momentum, which is quantized by the size of the box. So you look at all your many-body states, and you can see, well, I can account for all of them using the quasi-particles. If you can do that, you have a Fermi liquid. However, if you find that you get lots of low energy states that are not related to any quasi-particle that you know of, then maybe it's not a Fermi liquid. And that's in fact correct. So we have to do a little bit more than just counting ground state degeneracy, because it's a gapless system, a little more subtle.
Thanks.
Sure.
I have two questions.
Yeah.
They're a little related, but one thing is, like, typically for a correlation function, you can associate some sort of response function,
Yeah.
some fluctuation dissipation theorem between them at near equilibrium.
Yeah.
Is there some fluctuation dissipation theorem for, or what is like the associated like response function for this these like Green's functions? That makes, I don't know if this is a well-posed question, but
Yeah, no, there is a relationship between the, there are various spectral representations that allow you to go between time-ordered and anti-commutators and commutators. Yeah. Yeah, I don't want to go into that. There's a lot of technology with that. Yeah, we won't cover that here. We won't need that.
the other question I have is, so we're starting here from like a system without any disorder, but like if you start off in a disordered system and then turn down interactions, can you still define like quasi-particles even though you don't have momentum or anything like that? Like conceivably there's some sort of, is this like...
Yes, so that's an excellent point, and which none of the textbooks go into. Just if you took this definition here, like you said, where, okay, you look for this discontinuity, you see it, I have a Fermi liquid. But suppose momentum is not a good quantum number. Would you still have a Fermi liquid?
Yeah.
Well, so it turns out the answer is yes, but it's much harder to tell. But formally, the way you would say that you have is you have to go back to the defining definition of a Fermi liquid. That is, suppose you could still use this formula where P was not a momentum label, was some other label. I don't know, some label talking about some complicated eigenstate in the presence of disorder. You have some single particle, quasi-particle states. Here we know that the quasi-particles are labeled by a central mass momentum. But in a disordered system, they'll be labeled by some other quantum number. With some quantum number which ranges over n values, where n is the size of the system, that's just like momentum. Yeah, and if you could build up many body states and compute the energy using an expression like this, then you would say you have a Fermi liquid, a disordered Fermi liquid. Yeah. And there's another huge theory for that. Now it turns out that when you go to compute the lifetime of a disordered quasi-particle, so what we found at the lifetime in the presence of momentum conservation, the lifetime of a clean quasi-particle, at least I give you a rough argument, when as 1 over temperature squared. If you do this for a disordered Fermi liquid, and this is the, I guess, related to famous work by Altshuler, Aronoff, and so on, the lifetime of a disordered quasi-particles in 3 dimensions anyway, it doesn't go as 1 over temperature squared, it goes 1 over temperature to the 3/2. It's still faster than 1 over temperature. So it's fine. It's still a Fermi liquid, but it's slightly less stable. In 2 dimensions, the lifetime actually goes as 1 over temperature, and then all else help make it loose. You don't really have a Fermi liquid because you can have disorder affects localizing quasiparticles, it can become a very complicated business in 2D.
Yeah, thank you.
But these are not topics we'll cover in this course. Excuse me. All right. Well, that's fun discussion, and some of it is at a fairly high level for, especially for those who may not have taken 295B. But no worries, you know, the whole purpose of this chapter was just to get your familiarity of what Fermi liquid theory is about. You're not going to use it, and I'm pretty sure the rest of the course, yeah, we will be using methods that I won't need to appeal to tricks that you have to learn in 295B. But do follow the sections that how you've been doing that those methods we're going to use a lot. Okay, so I should also say on Monday there's no lecture because it's a holiday, Labor Day. But I will have the review session tomorrow morning at 9 a.m. And there won't be a review session on Tuesday because there's no lecture on Monday. And I'll see you next in lecture then on Wednesday.
Thank you.
Okay. So have a great weekend.
Thanks.
Thank you.
You too.
Good night.